Okay, so 19.1, day number 2, we're going to use vector addition and subtraction and look at some fun stuff with that. Okay, for each of the following, there's only one of them, so I'll do it once. Complete the diagram by drawing vector AB plus BC. Well, here's AB. Here's BC. Conveniently, they're oriented head to tail there. So AB plus BC would be the vector connecting the tail of AB to the head of BC. Sure. All right, so this would be vector AB plus BC. So what would the magnitude of AB plus BC represent? The what? The what between those 2 points? The distance. Okay, so I've got options. I can either use Pythagorean theorem, law of cosines, law of sines. In this case, conveniently, oh my gosh, this is 45, so this is 45. Since this easterly direction and that easterly direction are parallel lines, that's also 45, which makes this a 90. Lucky. You got a 90 on there? Gosh, that never happens, except today. Okay, so I got myself a right triangle with a length of 15 kilometers, a length of 10 kilometers, and I want to find that length. Well, Pythagorean theorem would tell me that 100, which is 10 squared, plus 15 squared, which is 225. So 100 plus 225 will equal r squared. So that's 3 1/4. If I took the square root of that, I think I get, what goes in that? 25 goes into that. 25 goes into that 13 times, I think. So then the square root of 25 is 5, and I get 5 root 13 for that distance. So the magnitude in part 2, the magnitude is 5 root 13. If you were a child that just decided they didn't like that, and they either put it in decimal form or left it in this form here, I mean, you wouldn't get elegance points, but you'd probably get the answer right. Okay, sadly. Okay, that's not very elegant. It's not simple. I get that. So let's do this. Okay, an aircraft is flying at 240 kilometers in a northerly direction. Let me draw that. Here's our aircraft. 240 kilometers per hour, straight north. Okay, I'm going to duplicate that too, so that I can do it for both examples, 1 and 2. Duplicate. Oh no, that's a D. Let's do this. There it is. Okay, so let's look at the 2 examples. If it encounters a 40-kilometer wind that's coming from the north, our resultant vector would be that one, right? Tail of the first, head of the second. What would be the resultant magnitude? Yeah, 200 kilometers per hour. Okay, so that was convenient. But now the wind is coming from the northeast. So if it's coming from the northeast at the same speed, I know this angle. That angle would be 45. Come on now. Ungroup. Ungroup that. I want to move that over. Okay, now my resultant vector is no longer heading due north. Okay. Okay, so in this case, in order to find the magnitude here, I would have to use law of cosines. All right, so I'm not going to go through the extent of this problem, but that length, right, c squared, we'll call this c. C squared would equal a squared plus b squared minus 2ab times the cosine of the angle in between. All right, and that would give us our side length. That would be our magnitude. That would be the speed at which we're traveling in that direction. next step to this in part 2 is to give a direction. So, or excuse me, in part B of 2. So for part 1 over here, part A was the sketch. Part B, what would that be? What's the direction in part A? Or in part 1? Still heading due north, right? So still heading north. Now in number 2, or part 2, right? Part A, I got my sketch. Part B, that angle is going to change. I'm going to just make up the angle because I don't want to do all the math right now. Are you okay with that? Yeah? Okay. I'm going to make it up. Let's make it up. I don't know. Let's go with like, what do you think? 26 degrees? Yeah. Okay, look decent? Right. Those of you at home, I know I'm a bad teacher, but I'm just not doing it right now. I just want to model whatever. Okay. So if that angle is 26, there's 2 ways I could write it. I could write it north, 26 degrees what? West. Now we're talking bearings, right? Or instead of just heading north, straight north, and turning west, I could head north and turn east. How many degrees? Blank degrees true, right? True bearing is you face north and you rotate east until you hit your bearing. It'd be 26 degrees short of 360, right? So that'd be what, 334? 334 degrees true? Okay, either of those bearings would work. Now that's under the assumption that that's the correct angle there, which I don't know if it is, I just guessed. Yeah, okay. Okay, not exactly sure why this slide is here, seeing that it's totally unrelated to what we're doing. But in case you're curious, you guys curious? Yeah? Oh, yes, you're curious, or you're faking the enthusiasm. Eddie's like, I like that problem about as much as I like the White Sox. Yeah, okay, which is a lot. Okay, this problem is actually relatively simple, kind of. Could I write 8 as 2 cubed? Oh, okay. Oh, that's not too bad. Could I bring this 3 up here? Yeah, I could. Oh, that's so cute. Oh, that's 3 to the 3rd. That's 27. I know, I'm so good at this. Oh, now what happens when the base and the base of the log are the same? Yeah. That's the answer. Right? Remember that? When the base of the exponent and the logarithm in its exponent are the same, it just kind of poof goes away. And then guess what? W equals, I don't know what that is, 189 maybe? Could somebody confirm that on a calculator? Okay, review of logs. That was pleasant. Oh, round trip puzzles. No, you don't have logs in this unit. I don't know. I honestly don't know why that slide is there. Yeah, that's from first semester. Yeah, that was like November, wasn't it? Something like that. Okay, let's talk details of vectors. When you add vectors, you always go head to tail. Okay, so head of the first vector to the tail of the second. Here is A plus B. Here's A plus B. Yeah? Well, that's not A plus B. That's A plus B. Well, you know what's true? That's the same as B plus A. Oh, that's weird. That's weird. That's a parallelogram. So the parallelogram method or the triangle method both work. They both get you to the same spot. You could travel either direction along the parallelogram and still get to that resultant vector. So all that told us was that the first way we got there was A plus B. Got there. Or we could go B plus A. Oh. Fun. Let's do more. Okay, here are a few properties. I know. If A plus B exists, you have closure. That's the closure property. It exists. You're like, what? Yeah, just take it. Okay, just absorb that. Okay, commutative property. A plus B and B plus A, they're the same. Yep. Moving along, associative property. If I take A plus B plus C, that's the same as A plus B plus C. You're like, what? Yeah. If I go from A to B, and then I go from there to C, that's the same as going from, what? Grace, did I confuse you?
You're not going to be.
C, Charlie.
Yeah. That's the point.
Or I use the vector C to get to a new location. Yeah. Okay, and then the additive inverse. Oh, I can't forget the additive identity. If you go along vector A and then you don't go anywhere else, it's the same as just going along vector A. Yep, I know. You're like, wow, you really do earn your 300,000 a year, don't you? Yes, today especially. And the last one, if you go to A and then you go the opposite direction of A, you end up where you started. Called the additive inverse. Cool. Waiting.
Yeah.
Commutative? Yeah.
I had to cross out. I had to cross associative.
This is so pleasant, you guys. Oh, so pleasant. Okay, so I'm gonna take A and B. I'm gonna add them. We know how to do that. Here's A plus B. Jean and Jean. So there's A plus B. Vector A plus vector B. Now if I take A minus B, like I'm supposed to do here in part A, what I do is I take the same magnitude but in the opposite direction for B. So A minus B comes out to be this other vector, right? I mean, this is, you got to be saying to yourself, this is great. Right? If I take, let's say, for instance, in part C, if I take B and I double it, what happens to its magnitude? It doubles. What if I take A and I multiply it by -3? It triples the magnitude, but then does what to the direction? Just flips it. That's it. There's nothing difficult about this other than just making sure that you don't screw up the algebra. So let's move on to an example on the next page. Not that one. Yeah, there's some algebra, which we'll get to later. This slide, all I really want to emphasize is that if I have this vector A, let me call that A, what would 2A look like? Yeah, just double that, right? So it'd be A twice. That'd be 2A, right? And what would negative 1/2 A look like? Yeah, other direction with half the magnitude. So that'd be negative 1/2 A. Let's see. Yeah, that'd be negative 1/2. And I know, so we've kind of hit on this, right? K is greater than 0. It's going to change the magnitude. Well, it's going to change the magnitude, but it's going to keep the same direction. Here, we would change the magnitude and alter the direction. And then here, what would happen? Poof, it just disappears. Right? If K is 0, then the vector disappears, right? And it has no magnitude. And the 0 vector has no direction, and it has no magnitude. Some people think that the 0 vector has a magnitude and a direction. No. I don't think that can be argued logically. Okay, and we're to the homework. Would you like to do a couple problems? Okay. Let me pause and talk about this for a moment.